The United Nations World Water Development Report is UN Water's flagship report on water and sanitation issues, focusing on a different theme each year. The report is published by UNESCO on behalf of UN Water, and its production is coordinated by the UNESCO World Water Assessment Program. Launched in conjunction with World Water Day, the report provides decision makers with knowledge and tools to formulate and implement sustainable water policies. The 2020 edition of the WWDR, titled Water and Climate Change, illustrates the critical linkages between water and climate change in the context of the broader Sustainable Development Agenda. Supported by examples from across the world, it describes both the challenges and opportunities created by climate change and provides potential responses in terms of adaptation, mitigation, and improved resilience that can be undertaken by enhancing water resources management, attenuating water-related risks, and improving access to water supply and sanitation services for all in a sustainable manner. It addresses the interrelations between water, people, environment, and economics in a changing climate, and demonstrating how climate change can be a positive catalyst for improved water management, governance, and financing to achieve a sustainable and prosperous world for all. The latest edition of the WWDR is the result of a concerted effort between the chapter lead agencies and those who gave regional perspectives. The report also benefited to a great extent from the inputs and contributions of several other UN Water members and partners, as well as from dozens of scientists, professionals, and NGOs who provided a wide range of relevant material. To learn more about all the authors and contributors, please see the full report online. Climate change will affect the availability, quality, and quantity of water for basic human needs, threatening the effective enjoyment of the human rights to water and sanitation for potentially billions of people. The hydrological changes induced by climate change will add challenges to the sustainable management of water resources, which are already under severe pressure from many regions in the world, and amplifies water-related extremes such as flood and droughts. Global water use has increased by a factor of 6 over the past 100 years and continues to grow steadily at a rate of about 1% per year as a result of increasing population, economic development, and shifting consumption patterns. Changes in precipitation and temperature, as seen in Figure 8, will directly affect the terrestrial water budget. Combined with a more erratic and uncertain supply, climate change will aggravate the situation of currently water-stressed regions and generate water stress in regions where water resources are still abundant today. Evaporation from the land surface is expected to increase as a result of the global trend of rising air temperatures in all but the driest regions, where the lack of water prevents such an increase. This increase may be offset by an increase in precipitation, but in many regions, and especially in those areas where rainfall volumes will decrease, this leads to decreasing stream flow volumes and a decrease of water availability in different seasons. Physical water scarcity is often a seasonal phenomenon rather than a chronic one, and climate change is likely to cause shifts in seasonal water availability throughout the year in several places. Climate change projections indicate with high confidence that extreme precipitation events will become more intense and frequent in many regions, but also that heat waves will occur more often than last longer, as seen in Figure 6. The former will increase global flood risk, while the latter is expected to make droughts more intense. Beyond water stress and the increasing frequency and magnitude of extreme events, climate change manifests itself, amongst others, through impacts on water quality, for example, through pollution and pathogenic contamination caused by flooding or by higher pollutant concentrations during drought. Many ecosystems, particularly forests and wetlands, are also at risk. Much of these impacts will be manifested in the tropical zones where most of the developing world can be found. Small island developing states are typically environmentally and socio-economically vulnerable to disasters and climate change, and many will experience increasing water stress. Across the planet, drylands are expected to expand significantly. Accelerated melting of glaciers is expected to have a negative effect on the water resources of mountain regions and their adjacent lowlands. Despite the growing evidence that the changing climate will affect the availability and distribution of water resources, some uncertainties remain, especially at local and basin scales. While there is not much disagreement about the temperature increases, which have been simulated by different general circulation models, GCMs, under specific scenario conditions, more variability and ambiguity exist in projected precipitation trends. Often, trends in extremes, like heavier precipitation, heat, prolonged droughts, show a clearer direction than trends in annual precipitation totals and seasonal patterns. Adaptation and mitigation are complementary strategies for managing and reducing the risks of climate change. Adaptation encompasses a combination of natural, engineered, and technological options, as well as social and institutional measures to moderate harm or exploit beneficial opportunities from climate change. Adaptation options exist in all water-related sectors and should be investigated and applied where possible. Mitigation comprises human interventions to reduce the sources or enhance the sinks of greenhouse gases. While mitigation options are also available across every major water-related sector, they remain largely unrecognized. Climate change generates additional risks to water-related infrastructure, requiring an ever-increasing need for adaptation measures. For water storage infrastructure, there is a need to reassess the safety and sustainability of dams and to evaluate them for potential modifications or decommissioning for the minimization of their environmental and social impacts and for the optimization of their services. In many regions of the world, groundwater and aquifers present the largest storage capacity, often orders of magnitude greater than surface water storage. It is increasingly necessary to consider unconventional water resources in future planning. Desalination can augment freshwater supplies, but it is generally energy intensive and thus may contribute to GHG emissions if the power source is non-renewable. Atmospheric moisture harvesting, such as fog water collection, presents a low-cost and low-maintenance approach for localized areas where advective fog is abundant. Water reuse, or reclaimed water, is a reliable alternative to conventional water resources for a number of uses, provided that it is treated and or used safely. Improved approaches to the treatment of water, and especially wastewater, also offer a range of mitigation opportunities. The bulk of GHG emissions related to water management and sanitation either originates from the energy used to power the systems or the biochemical processes involved in water and wastewater treatment. Increasing water use efficiency and reducing unnecessary water consumption and water loss both translate into lower energy use and thus lower GHG emissions. Untreated wastewater is itself an important source of GHGs, with more than 80% of all wastewater globally released to the environment without treatment. Treating its organic matter prior to its release can reduce GHG emissions. The reuse of untreated or partially treated wastewater can reduce the amount of energy associated with water extraction, advanced treatment, and in cases where the wastewater is reused at or near the release site, transportation. The biogas produced from wastewater treatment processes can be recovered and used to power the treatment plant itself, rendering it energy neutral and further enhancing energy savings. Wetlands accommodate the largest common stocks among terrestrial ecosystems, storing twice as much carbon as forests. Taking into account that wetlands offer multiple co-benefits, including flood and drought mitigation, water purification, and biodiversity, their restoration and conservation is of critical importance in terms of climate change mitigation. Global floods and extreme rainfall events have surged by more than 50% this decade and are now occurring at a rate 4 times higher than in 1980. Other extreme climatological events such as storms, droughts, and heat waves have increased by more than a third this decade and now are being recorded twice as frequently as 1980. Figure 15 shows the increasing trends in flood-related disasters globally, as well as meteorological and climatological events. Although these trends concern nearly all countries, the extent to which countries are affected is very much dependent on their level of socio-economic development. The range of available climate change adaptation and disaster risk reduction strategies include hard, like structural, and soft, like policy instrument, approaches. Hard measures include enhanced water storage, climate-proof infrastructure, and crop-resilient improvements through the introduction of flood and drought-resistant crop varieties. Soft measures include food and drought insurance, forecasting and early warning systems, land use planning, and capacity building, such as education and awareness. Hard and soft measures often go together. Urban planning, for example, can help increase resilience to flood risks by featuring drainage systems that provide spaces to safely collect and store floodwater. The city thus acts like a sponge, limiting surges and releasing rainwater as a resource. Modern communication methods such as social media and mobile phone services provide significant opportunities to help improve communication and early warning effectiveness. Drought and flood monitoring systems are also an important component of risk reduction. Mainstreaming gender and community involvement in decision-making processes are key elements to DDR strategies. Improved interagency coordination in water resources and disaster risk management is needed, especially in transboundary basins where it remains fragmented throughout most of the world. Anticipated water-related health impacts of climate change are primarily food, water and vector-borne diseases, deaths and injury associated with extreme weather events such as coastal and inland flooding, as well as undernutrition as a result of food shortages caused by drought and floods. Mental health impacts associated with illness, injury, economic losses, and displacement may also be substantial, although difficult to quantify. At the end of the Millennium Development Goals period, which was the years 2000 to 2015, 91% of the global population used an improved drinking water source, and 68% used improved sanitation facilities. Much remains to be done to reach the new, higher levels of safely managed water supply and sanitation services as defined under the SDGs for the 2.2 billion and 4.2 billion people, respectively, who lack this superior level of service. Climate change is likely to slow or undermine progress on access to safely managed water and sanitation and lead to ineffective use of resources if system designs and management are not climate resilient. By extension, progress on the elimination and control of water and sanitation-related disease will also be slowed or undermined by climate change. The specific challenges for agricultural water management are twofold. The first is the need to adapt existing modes of production to deal with higher incidences of water scarcity and water excess, like flood protection and drainage. The second is to decarbonize agriculture through climate mitigation measures that reduce GHG emissions and enhance water availability. The scope for adaptation in rain-fed agriculture is determined largely by the ability of crop varieties to cope with shifts in temperature and to manage soil water deficits. Irrigation allows cropping calendars to be rescheduled and intensified, thus providing a key adaptation mechanism for land that previously relied solely on precipitation. Agriculture has two main avenues for mitigation of GHGs: carbon sequestration through organic matter accumulation above and below the ground, and emission reduction through land and water management, including adoption of renewable energy inputs such as solar pumping. Climate-smart agriculture, CSA, is a recognized suite of well-informed approaches to land and water management, soil conservation, and agronomic practice that sequester carbon and reduce GHG emissions. CSA practices help to retain soil structure, organic matter, and moisture under drier conditions and include agronomic techniques, including irrigation and drainage, to adjust or extend cropping calendars to adapt to seasonal and interannual climate shifts. The water-related effects of climate change generate risks to business and power generation. Water stress can put a halt to manufacturing or energy generation. Impacts will also carry into operational aspects affecting the supply of raw materials, disrupting supply chains, and causing damage to facilities and equipment. Energy is in the spotlight of climate change initiatives, as about 2/3 of the world's anthropogenic GHGs come from energy production and use. There are a number of opportunities to mitigate GHGs and reduce water use at the same time. Reducing energy demand and increasing energy efficiency are starting points. One promising direction is the increased use of low-carbon renewable energy technology with little water requirements, such as solar, photovoltaic, and wind, the costs of which are becoming increasingly competitive with fossil fuel energy generation. While hydropower will continue to playing a role in climate mitigation and adaptation of the energy sector, the overall sustainability of single projects needs to be assessed, taking account of potential water consumption through evaporation as well as GHG emissions from reservoirs, not to mention the potential ecological and socio-economic impacts. For business, water stress is one of the main drivers for water reuse and efficiency. In concert with technology, a facility could look at day-to-day operations, such as the use of wash water and better monitoring and leak detection. On an expanded scale, a company might evaluate its water footprint and include those of its suppliers, which may have a far-reaching effects if they are large water users. The impacts of climate change on urban water systems include higher temperatures, reduced precipitation, and more severe drought on the one hand, and increasing heavy precipitation and flooding events on the other. It is precisely these extremes that make the planning of urban space and the provision of infrastructure so difficult. However, the need to develop climate-resilient urban water infrastructure remains critical worldwide, even in the most developed countries. The physical infrastructure for delivery of water and sanitation facilities can also be disrupted, leading to contaminated water supplies and the discharge of untreated wastewater and stormwater into living environments. Vector-borne diseases such as malaria, Rift Valley fever, leptospirosis, and others are often observed after flooding events. Urban water resilience goes way beyond the traditional city boundaries. In cases where water supplies rely on distant watersheds, planning needs to look well beyond the city's boundaries and consider the long-term impacts of urban expansion on distant freshwater ecosystems and the local communities that rely on them. Adaptation and mitigation actions by one sector can directly influence its water demand, which can in turn augment or reduce the local regional water availability, including quality, for other sectors. In cases of reduced water demand, such actions can lead to multiple benefits across sectors and boundaries, whereas increased water demand can result in the need for trade-offs over the allocation of limited supplies. Water use requires energy. Therefore, any reduction in water use has the potential to reduce the energy demand from the water sector and thus help mitigate climate change, if said energy source is from fossil fuels. Water efficiency measures in agriculture can increase water availability and reduce the energy needed for pumping, in turn further reducing the water needed for energy production. Increased use of renewable energy in agriculture, for example, solar PV pumps, provide additional opportunities to lower GHG emissions and to support the livelihoods of smallholders. Reducing food loss and waste could also have significant repercussions on water and energy demand and thereby reducing GHG emissions. Conservation agriculture allows soils to retain more water, carbon, and nutrients with additional ecological benefits. The biomass in soils of properly managed forests, wetlands, and grasslands provide mitigation opportunities through carbon sequestration and significant additional benefits in terms of nutrient cycling and biodiversity. And as described earlier, improved approaches to the treatment of water, and especially wastewater, offer an additional range of mitigation opportunities. Both climate and water management require mechanisms for oversight and coordination. Sectoral fragmentation and bureaucratic competition may pose serious challenges for the integration across scales. This calls for 1. Greater public participation to discuss and manage climate risk, 2. Build adaptive capacities at multiple levels, and 3. Prioritizing risk reduction for socially vulnerable groups. Greater public participation to manage climate risk is suggested as a way to build adaptive capacities at multiple levels, avoid institutional traps, and prioritize risk reduction for socially vulnerable groups. At the same time, scientific information and data also need to be made available at the local level and included as information into local multi-stakeholder decision processes. While governments remain responsible for leading national climate mitigation and adaptation measures, as well as water governance, the process of change is always co-produced. There are clear indications that many young people are increasingly concerned about climate change. Cities have also become forerunners of climate action in many countries, and leading companies have made commitments to reduce their water footprint and GHG emissions in order to address their contribution to water stress and climate change. Poverty, discrimination, and vulnerability are closely related and typically intersect. Women and girls from minority ethnic groups or from remote or disadvantaged areas may suffer multiple forms of exclusion and oppression. When disaster hits, such inequalities can become exacerbated, making it more likely that poor people are affected. Poor people are also likely to lose relatively more than the non-poor. Finally, as 60% of global fresh water flows cross-national boundaries, transboundary cooperation is essential for effective measures towards climate change adaptation and mitigation. Food security, human health, urban and rural settlements, energy production, industrial development, economic growth, and ecosystems are all water dependent and thus vulnerable to impacts of climate change. Climate change adaptation and mitigation through water management is therefore critical to sustainable development and essential to achieving the 2030 Agenda's Sustainable Development Goals, the SDGs, the Paris Agreement on Climate Change, and the Sendai Framework for Disaster Risk Reduction. Within the 2030 Agenda, water serves as an often unacknowledged but essential connection factor for attaining the different Sustainable Development Goals. As such, failure to adapt to climate change not only puts the realization of SDG 6, the water goal, at risk, it also jeopardizes the achievement of most of the other SDGs. And while SDG 13, Take Urgent Action to Combat Climate Change and Its Impacts, includes specific targets and indicators, there is no formal mechanism linking SDG 13 to the goals of the Paris Agreement, resulting in parallel processes. Although water is not mentioned in the Paris Agreement per se, it is an essential component of nearly all the mitigation and adaptation strategies. However, water is identified as the number one priority for adaptation actions in most of the intended nationally determined contributions, the INDCs, and is directly or indirectly related to all the priority areas. Similarly, water is hardly mentioned in the Sendai framework itself, even though water flows through each of the priorities for action and is central to all of its 7 targets. The challenges of development, poverty eradication, and sustainability are intricately interwoven with those of climate change mitigation and adaptation, especially through water. Given water's role in mitigation and adapting to climate change, water could play a connecting role across the SDGs and across policy frameworks such as the Paris Agreement. While the need to address climate change through water is well recognized, this is not being translated into concrete action. In the nationally determined contributions, the NDCs, submitted by countries as part of the Paris Agreement, water is, in many cases, recognized in terms of policy statements or broad strategies, usually in terms of adaptation, but few NDCs actually include the intention to prepare a specific water plan. And while a majority of countries acknowledge water in their NDC's portfolio of actions, fewer have estimated the related costs of these actions, and even fewer have included detailed water-related project proposals. Clear synergies between adaptation and mitigation opportunities through water are practically non-existent in the NDCs. Water resources management and water supply and sanitation services are currently underfinanced and in need of greater attention from governments. Although there are significant sources available from the climate change funds, most of that has been earmarked for mitigation and has thus not been available for financing water interventions which have generally been considered from an adaptation perspective. However, there are increasing opportunities to more genuinely and systematically integrate adaptation and especially mitigation planning into water investments, rendering these investments and associated activities more appealing to climate financiers. This trend could be particularly advantageous as mitigation made up 93.8% of climate financing in 2006, but water projects consisted of a fraction of 1% of that sum. Furthermore, various water-related climate change initiatives can also provide co-benefits such as job creation, improved public health, reduced poverty, the promotion of gender equality, and enhanced livelihoods, among others, further strengthening their bankability in the eyes of financiers. The challenges in terms of technological innovation, knowledge management, research and capacity development are to promote the generation of new tools and approaches through advanced research and development, and equally as important, to accelerate the implementation of existing knowledge and technologies. Satellite-based Earth observation can help identify trends in precipitation, evapotranspiration, snow and ice cover melting, as well as runoff and storage, including groundwater levels, while remote sensing can reveal large-scale processes and features that are not easily observable via traditional methods. The temporal and spatial resolution may not be fully adequate for smaller-scale applications and data analysis. However, when backed with national statistics, field-based observations, and numerical simulation models, remote sensing can contribute to a comprehensive assessment of climate change impacts related to water. Applications of big data analytics can help to obtain knowledge by processing the collection of continuous streams of water-related information and data in order to extract actionable information and insights for improved water management. Citizen science and crowdsourcing have the potential to contribute to early warning systems and to provide data for validating flood forecasting models. Despite the mounting evidence that climate change is affecting the global hydrological cycle, much uncertainty remains when projecting its impact over smaller geographical and temporal scales. However, this uncertainty must not be seen as an excuse for inaction. Rather, it should serve as an impetus to expand research, to promote the development of practical and analytical tools and innovative technologies, to adopt no-regret approaches, and to build the institutional and human capacity required to foster informed, science-based decision-making. The need for greater cooperation between the water and climate communities exists well beyond the realm of scientific research. On the one hand, it is imperative that the climate change community, and climate negotiators in particular, give greater attention to the role of water and recognize its central importance in addressing the climate change crisis. On the other hand, it is equally, if not more, essential that the water community focus its efforts to promote the importance of water in terms of both adaptation and mitigation, develop concrete water-related project proposals for inclusion in nationally determined contributions, and strengthen the means and capacities to plan, implement, and monitor water-related activities in NDCs. Combining climate change adaptation and mitigation through water is a triple win proposal. First, it benefits water resources management and improves the provision of water supply and sanitation services. Secondly, it directly contributes to combating both the causes and impacts of climate change, including disaster risk reduction. Third, it contributes directly and indirectly to meeting several of the Sustainable Development Goals: hunger, poverty, health, energy, industry, climate action, and so on, not to mention SDG 6, the water goal itself, and a host of other global objectives. In an era characterized by a host of gloom and doom studies and articles on climate change and other global environmental crises, this report proposes a series of practical responses in terms of policy, financing, and action on the ground to support our collective objectives and individual aspirations to achieve a sustainable and prosperous world for all.